In this video, we are going to look at bubble sort, one of the simplest sorting algorithms, as our first example of sorting algorithm. In later videos, we are going to look at other sorting algorithms that are more advanced and more efficient. But for this video, bubble sort, we are going to look at how it works, what is the main idea, and we are going to go through an informal argument on why it works. And we are going to see its implementation in C++ and also its time complexity for the worst case and base case scenarios. So let's start with the main idea. It's a very simple idea. And because of that, you will see that its implementation is going to be very straightforward as well. Okay, so what is the idea? The idea is that we only look at adjacent values in the sequence. So you have a sequence of elements and you want to sort them from the smallest to the largest. And in bubble sort, we only compare adjacent elements in the sequence. And if they're in the wrong order, if between the two adjacent values, the first one is greater than the second one, then that's the wrong order. In that case, we swap them. And that's it. We repeat this until the entire array is sorted. So as you see, it's a very simple idea. So we swap adjacent elements that are in the wrong order. Okay, so if the first one is greater than the second one, then that's the wrong order. And we do this until the entire sequence is sorted. Okay, now I'm going to start an example here, but because it's, it takes time to do the updates on the board, then I'm going to use a website to show you the rest of the steps. But let's start here with a small array of size 6, for example. Okay, so 0, 1, 2, 3, 4, and 5 are the indices, and then the elements of the array, the values, let's say they are 10, 7, 15, 1, 4, and 9. Okay, so what we do is we start with the first two elements, so 10 and 7. We compare them and make sure that they're not in the wrong order, which they are in this case. 10 is greater than 7, so it shouldn't be before 7. So in that case, we need to swap them, right? So we swap 10 and 7. So 7 goes here and 10 goes here. Okay? Then we look at the next two adjacent values, 10 and 15. And we make sure that they're in the right order, which they are. 10 is less than 15, so they're good. So in that case, we don't swap them, and we move on to the next pair of values, namely 15 and 1. Now, obviously, 15 and 1, the adjacent values are in the wrong order because 15, which is greater than 1, is supposed to come after 1. So in that case, again, we swap them. So this becomes 1, this becomes 15, and you get the idea, right? So at any given moment, we are looking at two values that are adjacent. We compare them. If the first one is greater than the second one, we swap them and we move on to the next pair. But if not, if the first value is less than or equal to the second value, then we don't need to do anything. We just ignore and move on to the next pair. Now, how many times do we need to do this and all of that? We are going to look at that in a moment. Okay, now take a look at this example. So we have an array of size 10, indices from 0 to 9, and the elements are 11, 4, 14, and so on. Now, again, we want to run bubble sort. So we compare the first pair, 11, 4, and 11 is greater than 4, which means that they're in the wrong order. So what we do is looking at 11 and 4, we need a swap here, so we swap them. Then we move on to the next pair, 11 and 14. 11 is less than or equal to 14, so we're good here. We move on to the next pair, 14 and 8. And 14 is greater than 8, which means they're in the wrong order, so we swap them again. Then we move on to the next pair, 14 and 43. They're in the right order, so we don't move them, right? And now we move on to the next pair. Now, from now on, I want you to pay attention to what happens to 43, which happens to be the greatest value in the sequence, right? 43 and 22. 43 is greater than 22, which means they're in the wrong order, so we swap them. And then we have 43 versus 17, again, wrong order, so we swap them. And then 43 and 20. 43 is greater than 20, which means these two are in the wrong order, so we swap them. Now you're looking at 43, what's happening? So it's just, going to the right over and over. 43 and 31, again, 43 is greater than 31, so they're in the wrong order, so we swap them. And finally, the last pair, 43 and 25, 43 is greater than 25, so it should be after 25, so we have to swap them. And this is called one pass through the array. And now the thing that when I told you that, follow what's happening to this particular number 43, which happens to be the greatest value in the sequence, and you realize that 43 was pushed from where it was originally, somewhere in the middle, all the way to the end of the sequence. And this is not a coincidence. It is going to be like this always, no matter what the values are. And by this way, what I mean is if you go one pass through the array, comparing every two adjacent values and swap them if they're in the wrong order, and you do this all the way to the end, what happens at the end is that the greatest value will be pushed all the way to the end of the sequence, where it belongs in the sorted version, right? And basically that's where the name bubble sort comes from, because this number here, 43, wherever it is, it's kind of like a bubble that, goes from the bottom of a liquid all the way to the top. This 43 is going all the way to the end. So that's called one pass. Now, 43, which was the greatest value, is at its correct position. Now we start over from the beginning. Compare 4 and 11, right order. 11 and 8, you need to swap them. 11 and 14, they're good. 14, 22, they're good. 22 and 17, they need to be swapped. 22 and 20, again, we need to swap them. 22 and 31, we don't need to do anything. And finally, 31 and 25, they're in the wrong order because 31 is greater than 25, so we swap them again. And a similar thing happens in the second pass. You can see that 31, which is the second greatest value in the sequence, is pushed all the way to the position that it belongs, which is the second to the last position, right? So now the observation that we can make here is we can realize how many passes do we need. At the end of the first pass, the highest value was at its correct position at the end. At the end of the second pass, when we did this comparison and swapping all the way from the beginning to the end for the second time, the second highest value is pushed all the way to its correct position, which is the second to the last position. Now, if I repeat this again from the beginning, this time a little bit more quickly, you will see that 25, which is the third highest value, will be fixed to its position. No swap is necessary this time, and so on and so forth. So, in other words, um, um, that tells me how many times I need to go from the beginning to the end and check for adjacent pairs that need to be swapped. Okay, now let's go to our code and see how we can implement this idea. Okay, so I'm going to implement this algorithm as a function, and I'm going to use templates here. So type name T, because we can sort arrays of integers, arrays of type double, even characters, and so on. So I don't want to define different versions of bubble sort. which is going to be exactly the same function, and the only difference would be the type. So that's why we use templates here, right? So let's call this function bubble sort, and its first parameter is going to be the array itself of type t, where t can be int later on when we call this function, or double, or character. And then, of course, we need the size of the array. Okay, now we have the loop. So that's for n passes that we need. Remember, at the end of the first pass, the largest element goes all the way to the end. At the end of the second pass, the second largest, and so on. So I need n, not size, um, iterations or passes. And then for each pass, I have to start from the beginning. So j equals 0. And j is less than n minus 1 to the end, right? J plus plus. And what I do here is I compare the adjacent elements, so a at j and a at j plus 1. And if a at j is greater than a at j plus 1, then I need to swap them, right? So, because they're in the wrong order now. So, some programming languages have built-in swap, and C++ is the same. But if you want to implement it yourself, it's only 3 lines of code. So what you need is a temporary variable of type t that holds on to the value at aj. And then you say a at j, replace that with a at j plus 1. And finally, a at j plus 1 should be what? Temp, which was the value at j, at index j, right? So that's basically swapping a at j and a at j plus 1, and we only do that when they're in the wrong order, which means the first value is greater than the next value. I need an int here. And that's basically it. That's your implementation of bubble sort. Now, if you want to, you can define arrays like, example 1, like it can be an array of integers like 10, 2, 21, 13, and 4. And then we can call bubble sort on example 1 and its size, which is 1, 2, 3, 4, 5. And then after that, if you print the values in example 1, you'll see that they are in a stored order. So example 1 at index I, separated with comments, right? So I'll let you run this on your own, but yeah, if after doing this, you'll see that the values will be 2, 4, 10, 13, and 21. Okay, and because we use template here, we can use the same function for an array of a different type. So example 2 can be an array of characters because we can compare their values. So I can say, for example, C, comma, E, A, and then I can call bubble sort on example 2, comma, its size, which is 3. And then I can print the values after sorting them. So example 2 at index I, and put spaces between them. And again, if you run this on your own, you'll see that after calling bubble sort on this second array, the values, the characters will be sorted. So A will be the first one, then C, and then E will be printed. So HCE instead of CEN. So there you have it. That's the implementation of bubble sort. Now, what's left to do, and you can see, as I told you at the beginning, you'll see that it's a very basic implementation. There are ways to improve this a little bit, but at the end of the day, this is not going to be a very um, efficient sorting algorithm. The benefit is it's simple to understand how it works, and also it's easy to implement it. So what can we say about the efficiency? I told you several times that it's not the most efficient algorithm, but what is the time complexity or runtime of this algorithm? Let's talk about that. So let me very quickly write the code over here. So we have two nested loops, right? For I equals 0, I is less than n, I plus plus, and then you have for int j equals 0, j is less than n minus 1, j plus plus, and then inside this inner loop, what we do is we compare the value at index j with the value at index j plus 1, and if the first one is greater than the second one, then we swap them for a at j and a at j plus 1. Okay, and that's the end of the for loop, the end of the other for loop as well. So that's basically the piece of code that is responsible for sorting. Now, similar to the previous examples, I would like to start from the inside and work my way out. Okay, so let's take a look at this if statement and see if we can figure out what's the runtime for this piece of code. So my claim is that these two lines, the if statement and the body, the time that it takes for executing this piece of code once, so I'm not talking about any of the loops at the moment, just the if statement on its own. If you think about it, you can see that the time that it takes to execute this piece of code does not depend on the size of the array, or n. And the reason is, what is it that we are doing here? We are looking at the value at index j that in an array is independent from how small or large the array is. You can do that constant time, constant meaning doesn't depend on n. And then I'm doing that for j plus 1, again, constant time. And then comparing two values doesn't have anything to do with the size of the array. And also swapping them, if you remember, that's just like 3 steps of assignments, right? Defining a temporary variable and then a couple of assignments. So as I said, this entire thing, running this entire thing, requires the amount of time that it requires doesn't depend on n. Doesn't matter how small or large the array is, this is going to take the same amount of time. So I'm going to say constant time, and I'm going to call that c, that constant time c. Now, if you really want to know how many primitive steps we have here, we can be a little bit more precise and say, okay, looking up j's value, that's one primitive thing to do, one primitive operation. And then looking at this value in the array, the j plus first, that's another primitive operation. Then comparing those two values, that's another primitive. And then swapping them, that there are a few more there. So a few primitive operations. But again, that number of few primitive operations is not going to be the same always, because if aj is greater than aj plus 1, then we need to do what's inside. And if it's not, we just skip this and go to the next j. But in any case, it's independent from the size of the array. So that's what we mean by saying it's constant. Okay, so that's that. Now, working our way to the from the inside out, let's take a look at the inner for loop. Okay, so what is the number of iterations here? The number of iterations is n, or I'm sorry, n minus 1, right? From 0 to n minus 1. And at every iteration, we do this, which is some constant time. So the overall time needed for that is c plus c plus c plus c n minus 1 times, because we are repeating the same task n minus 1 times. So overall what we get is c times n minus 1 for the inner loop. Now, finally, we can talk about the outer loop, which is the entire thing. So now, what if I focus on the entire thing? Okay. How long does this take? And if you look at the outer for loop, the number of iterations this time is n, because it's the number of iterations is n, because the upper bound is n. So from 0 to n minus 1, including n minus 1, that's n iterations. And at each iteration, we do this much work. So I have to add c times n minus 1 by itself n times. So c times n minus 1 plus c times n minus 1 dot 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 c times n minus 1. And we are repeating this n times. N times. I don't know what happened to my board. But yeah, so we're repeating this n times. And therefore, what we get is c times n minus 1 times n, right? Adding c times n minus 1 n times, that gives you that. So that's the overall running time of this algorithm. So repeat it n times. Okay, so we can say T of n, the running time of bubble sort on an array of size n is c times n minus 1 times n for some constant n. And if you want to simplify this using asymptotic notation, which we talked about before, first we can distribute, and we get cn squared minus cn. Then, if you remember, there were two ideas when talking about asymptotic notations. One was constant coefficients do not matter. So c and c, we don't care about those. So we have n squared and n. And the second one was when we have more than one term added or subtracted, we only keep the one that is the most dominant one. So as n grows and becomes larger and larger, n squared dominates n. So at the end of the day, you can say the running time is order n squared, which is another way of saying that it's bounded by some constant times n squared. What the constant is, again, if you remember, we said it's machine dependent, and it depends on the programming language and a lot of other things. And that's basically the main reason that we use asymptotic notation, to not focus on those details, because we only want to talk about the time complexity of the algorithm itself, independent from its implementation. Okay, now, another thing that I want to tell you here is that when we talked about this swapping here, I told you that we don't do the swap all the time. We only do that when aj is greater than aj plus 1. In other words, if aj is less than or equal to aj plus 1, then there is no swap. So this constant time here will be only the time that it takes to look at aj and aj plus 1 and compare them. The swap is not included in those cases, right? Now, the best possible case that can happen is that the case where we are running bubble sort on an array that is already sorted. In that case, for every j, aj is going to be less than or equal to aj plus 1 because the array is sorted to begin with, which means we never go inside the body of the if statement and we never swap anything. That's the best case scenario for bubble sort. The fastest kind of, the input that the bubble sort runs the fastest on is when the array A, before we call bubble sort, is already sorted. In that case, aj is always less than or equal to aj plus 1. Every value is less than or equal to the next value because it is already sorted, which means that the condition of the if statement is always false, which means that we never swap anything, right? But still, we need to verify that by checking this with that, right? And that takes some constant time, a smaller constant, but nevertheless, it's a constant. Looking up this value, looking up this value, and then the comparison. So I'm telling you all of this to tell you that even in the best case, still, the same kind of analysis works for bubble sort. So the worst case running time. So for bubble sort, we can say the worst case scenario for the running time is order n squared. And the best case, when the input array is sorted itself without any of our swapping, still it takes order n squared time, even though we are not going to swap anything if we call bubble sort on a sorted array. So the best case time complexity and worst case time complexity for bubble sort is the same. It's not always like this. For some sorting algorithms, if the array is already sorted, then it takes much faster. And there are tricks that you can apply to bubble sort to catch that. But in this format that I showed you here, I implemented, it doesn't matter. It's always some constant. The constant is going to be smaller if it is sorted, but still some constant time n squared for the best case runtime as well. So we're almost done with bubble sort, except for one observation. And that observation is I'm going to go back to the animation that we had and start over. Okay, so the observation that I have here is the following. So we start from the beginning, we swap and swap and swap. And at the end of the first pass, when 43 is fixed at the end, the highest value is moved all the way to the end of the array where it belongs. Then we start our second pass, right? Now, the point that I want to make here is that in the second pass, when we are looking at adjacent pairs, we don't need to go all the way to index 9. We can stop at index 8. Why? Because 43, which is at index 9, is already and always the highest value after the first pass. So in the second pass, we can start at index 8. And if you see that, that's what's going to happen here. 22 and 20 are swapped, 31 and 25 need to be swapped. And now we don't even bother comparing 31 with 43. We stop right here because we already know that 43 is the greatest value. So there is no reason to compare it to 31, and we stop, right? And similarly, in the third pass, we start over from the beginning, and we can stop at index 7. We don't need to go to index 8 or 9 because we already know that what's at the last index is the highest, and what's before that is the second highest value. So we look at the adjacent elements, looking for swaps that might be necessary, only up to index 7. We don't go to index 8 or 9. Okay, so that is going to make your code do less iterations and make it run a little bit faster. So that's a simple improvement that can be applied to bubble sort. But let's see how that changes the code. Okay, so here we are. This was our implementation of bubble sort. So the outer loop is for the passes. So when I is 0, that's the first pass. When I is 1, that's the second pass through the array. The inner loop is responsible for how far we go and when we are comparing adjacent values. And you see that it already says n minus 1 because we are comparing aj and aj plus 1. So j should stop at n minus 1, and j plus 1 in that case becomes n minus 1, the last element, right? But now we say that when I is 0, we have to go all the way to the end. But when I is 1, in the next pass, we can stop at n minus 2. And then in the next pass, we can stop at n minus 3. And in the next pass, we can stop at n minus 4, and so on. So very simply, with a very simple fix, I can replace n minus I with n minus I minus 1. So as I goes up, my path stops at a lower index. In the first time, it goes all the way to the end. In the second pass, it goes to the one before the last element in the array, and so on and so forth. So that reduces the number of iterations almost by half. But even though this is an interesting fix and it improves the runtime and technically it kind of halves the runtime, still it will be in asymptotic notation it will be n squared, because basically what we are changing is this constancy. We are having the constant, or more or less. So if it was originally like 9 times n squared, now it becomes 4 times or 5 times n squared or something. But still, asymptotically, it goes to the same complexity class of um, order n squared. So there you have it. That's bubble sort. In the next videos, we'll see more advanced sorting algorithms. Some of them are more efficient than bubble sort, significantly more efficient than bubble sort.